Okay, so we're going to go into Chapter 10. Now, we've already talked about how to do some of this in class. Yes, we're going to kind of summarize some stuff and change it a little bit from the original guided notes, but we're going to get through this. So again, we're going to start dealing with curved data here. So if we have a scatter plot shows curved data, maybe it would be exponential growth. Maybe it's exponential decay. And if it is, it'd be of the form our predicted y equals a times b to the power of x. Or it could be a power function. That's where y equals a times x to the power of b. And in this case, a and b, both cases are still they're just numbers, they're constants. Now, what we can do with our data in these cases is we can linearize the data by taking advantage of logarithms. So what that'll let us do is they'll actually make some of our numbers smaller. It'll make our graphical displays easier to use, kind of more convenient to construct from. So we're going to try that first, and then go into how we can use a calculator to do these. So our definition is we have to remember about logs. And if you forgot about logs, it says log base b of x equals y if and only if b to the y equals x. A couple rules about this. X has to be greater than 0, b has to be greater than 0, and b is not equal to 1. Because 1 to the power of anything is just going to be 1. Now, our rules for logarithms. First, if we have log a times b, well, that's going to be equal to log a plus log b. We're going to take advantage of this rule. Log a divided by b, well, that's equal to log a minus log b. And the last rule we have is that log a to the power of p, well, that's equal to p times log a. Now, these are 3 rules so far you learned to have logarithms. We're going to take advantage of these when you start doing some manipulations. Now remember, y equals ab to the power of x. This is our exponential function. Well, if I take the log of both sides, I get log, oh, I came out of order. Let's get it up there. Log y is equal to log ab to the x. I can use our rule of logarithms to break down apart my right-hand side to log a plus log b to the x. I then apply the other rule of logarithms, so log b to the power of x becomes x times log b. This is a linear relationship. Log b is just a number, okay? It's going to be some number, so it's a constant. Since I now have a constant times x, I have a standard slope. It's a constant rate of change. That is a linear relationship between x and the log of y. Now, let's try it for our power function. If I take the, same thing happened. If I take the log of both sides of the power function, I have log y equals log ax to the b. Well, again, I take advantage of those same rules of logarithms. Log ax to the b becomes log a plus log x to the b. I can still apply that another rule of logarithms, so that log x to b becomes b times log x. This is also a linear relationship. B is a constant. Log A is just another constant. So I have a constant rate of change. But the linear relationship between the variables log of x and log of y, not between x and y. You excuse me, I have to mute the mic. I have a little bit of a cough every now and then. Now, let's go ahead and try to linearize some data. So I have a table of data here. It shows the distance from a heat source and the temperature measured. So if I have a distance of 1 centimeter, temperature measured 130 centimeters, or 130 degrees Fahrenheit, and so on. Let's go ahead and think about this. If one of these was going to be used as an explanatory variable, the distance is probably going to explain the drop-off in heat. So I'm going to use distance as x, temperature as y. I'm going to load these in my calculator. So go ahead, pause the video, take a moment, load this in your calculator. If you have me back, you should have gotten these loaded as L1 and L2. So first thing I'll do is plot the scatter plot. And if I do that, it looks like this. Clearly, I'm dealing with some curved data. The question is, what kind of curve is it? Well, if I run linear regression, this is what I end up with. that y hat is 121.61 minus 6.61 to the x. I'm sorry, times x. My r is negative 0.894. So my r squared is about 0.8. If I look at my residuals, clearly there's a pattern. As we've said in residuals, we don't want patterns in residuals. So I need to choose a more appropriate model. Well, I can try the exponential. What I'm going to do is I'm going to still keep x the same. I'm going to take the log of y. So I'm going to do in L3, I'm going to go up to the top and take the log of L2. So I go up to the top on 3, hit enter. I tell it, give me log of L2. And it fills in all those values for me. Now I scatter plot L1 and L3. Now if I look at this, I'm now plotting x against log y. Still kind of a curve. If I run linear regression on it, this is the line I end up with. This is the equation of the line I've ended up with. Now my r has gotten a little bit better. Negative 0.923, that's better than negative 0.89. My r squared has grown. Now I'm at 0.852, so I've accounted for 85.2% of the variability. And correlation is getting better. But if I look at my residuals, they still have a curve. So it looks like I'm still going to need a better model. Now, a lot of times what we would do is, if we have this, we would not use this model because we want to keep going until we get rid of patterns in the residuals. We won't always be able to do it, okay? But what we can do right now is we can do an inverse transformation on the equation, because right now, we'll go back and show it, it's giving me a straight line and trying to match it to that curve, my curve data. So instead, I have to transform my equation back so I can actually plot the curve to my data. So I had the log of y, and we know it's base 10. Well, if I want to do that, to get rid of that log base 10, everything becomes a power for 10. Now remember, log base b of x equals y, if and only if b to the y equals x. That's why I had to take 10 and put that as a base and raise everything to that. Use that as my base. So by using this rule, b log b of x, or b to the power of log b of x, equals x. So 10 to the log base 10 of y hat equals y hat. On the other side, I still have 10 to the power of 2.09 minus 0.03 to the x. So this is what our equation looks like. Okay. So I have 10 to the power of y1. It hasn't changed. I use that y1. That's my new equation. 2.09 minus 0.03x, 2.089. I've put all this in so that that's my power, 10 to the power of y1. Now I look at my original data. I put that curve on it. It's plotting y2 on that. Now, I can also try the power model. In the power model, we have the log of x against the log of y. So I still take L1, and now I'm going to load into L3. I'm going to take the log of L1. And in L4, I'm going to take the log of L2. I plot L3 and L4. And that looks a lot more linear than what I've been dealing with so far. That's a lot straighter, doing the log of 3, the log of x, and the log of y. If I run linear regression on it, end up with a pretty straight line. It's not too bad. It looks like it's hitting a lot of the points. I still get this from my equation. That's a really strong r and r squared. And those are my residuals. Now, it's not a perfect residual, definitely not random, but there's less pattern. Of course, in order for me to see what that curve would look like on the original data, transform back. So remember, I have my rules. I can apply these rules to solve. So my y hat, applying these rules, I end up with 10 to the power of 2.1 times x to the power of negative 0.255. I have to load these back into the y1, y2 to get my curve, and this is what it looks like. So this curve looks like it's going to be pretty good. I can use this as my model to make predictions now. So if I was 4.5 centimeters away from the heat source, that's an X. I want to know what would my temperature be. So take a moment, try playing your calculator, see what you got. And I end up with 85.79 degrees using that linear model. Okay. Now, we use log base 10. You can also use the natural log. Okay. Let's try some other ones, though. Okay. Remember, there is a shortcut for exponential growth. Okay. If you have a ratio among the data, and actually I misspoke this in class. I kept saying y divided by x. What you have is you have your scatter plots, you have all your x's, all your y's. You look at your later y's and see, are they going up by a common ratio? So if I take my fourth entry for y divided by the third entry for y, I'm going to get some ratio. I compare that to my third entry of y divided by the second entry for y, so on and so forth. If I see a common ratio turning up, that suggests to me I have exponential growth. Now, don't forget, we kept going back to residuals. Residuals are going to show me if I have the best model for a data set. And if it don't fit, you got to quit and try something else. Now, we also talked about how we can use a calculator to save us a lot of time on these. It's valuable to be able to be familiar with the logarithms, be able to use them and do the conversions and linearize it, can't speak today, and transform it back. However, the simple fact is we can use a calculator to save us a lot of time. If you practice with it, you can get to these answers really quickly. So we're going to do a regression analysis for this age and income data. So pause the video, take a moment, type it in your calculator. This is some of the stuff that we did in class before, but we want to try it again. Okay, so if you're playing, you must have this typed into L1 and L2, that we're going to try to make predictions about income using age as an input. So I took the time, I loaded into L4 and L5 in my calculator. So that's where my data is at. Yours can be in L1, L2. Some of your screens should look different than mine. My data is in L4, L5. So first thing is, in order for me to do this, I want to make a scatter plot of the original data. And doing that, don't forget to label it, I know my data is curved. I can see it. So what I'm going to do is I'm going to try the different curves and see which one works. Now in our calculator, all our different curves, let's turn that back on. We've been using StatCalc 8. Our different curves follow right behind it. We have the natural log regression, exponential regression, and power regression. So these are the three curves I need to compare my data against. This is a table I'm going to set up. I have my linear regression, which is StatCalc 9, exponential regression, StatCalc 0, and the power regression, StatCalc A. So I go down and calculate, run 9. This is how mine's going to be set up, and I'm storing the line just so I can see the curve later if I need to. And that's what happens if I run it. So this is StatCalc 9. First thing is it tells me my R squared is 83.83%, which is not a bad R squared. I can write my equation using exactly what it tells me on the calculator screen. Y equals A plus B times natural log of X. So income equals, or predicted income equals, negative 282.86 plus 94.26 times natural log of the age. So that's going to be my equation. I'm not going to transform it to linear. I already is a linear equation. My constant rate of growth is positive 94.26. There's a typo in my transformation. I shouldn't have changed my transformation. It should look the exact same as my equation. So there's a typo on my screen, which is just going to drive me nuts. We actually need to fix that. because it's going to be up there for the whole time. Because that is just going to drive us crazy staring at it the whole time. Okay, so it is linear. It is a linear equation. It's a linear equation of the log of x versus income. Well, of course, we got to look at our residuals. Look at our residuals. Clearly, there's a pattern in them, and it's a curve. So we go on to our next one, exponential regression or stat calc 8. Using this L4, L5, here's my findings. So my R squared is nice and high. 99.97% of the variability of income has been accounted for this way. This is what my equation would actually look like. Income equals 6.95 times 1.05 to the age. This is not a linear equation though. A linear equation would have a constant times the age, and that's not what I have. So I have to apply some of my rules of logarithms. I take the log of both sides of the equation. Using the rules of logarithms, log of a times b is equal to log a plus log b. I can expand the right-hand side. Finally, log of a number raised to a power is equal to that power times the log of the number. So I can bring that age down and make it a multiple. Now, I've already converted. Log 6.95 is just a number. It has to be 0.842. Log 1.05 is also just going to be a number. I put it inside of the calculator. I get it's 0.0221. So again, I use this for my equation, but when I transform it to linear, I end up with this. So using x, I have a linear model for the logarithm of income. So I can input age and get the log of income. Again, need to look at my residuals. Okay, that looks like a mess. There's not a clear pattern though, so it's pretty bad looking, and that's good. We want residuals that are ugly. However, I still need to run power reg just to make sure that's not going to be a better equation on the line. So I do. Stat calc A. I have my R squared is 0.976, so not bad, but not as high as exponential regression. I can get my equation, y equals a times x to the b, or in predicted income equals 0.76 times age to the 1.782. There's my equation then. However, in order to get a linear equation, I take the log of both sides. Applying our rules of logarithms, we can expand the right-hand side. Log 0.076, that's just a number. Log age to a power, I can bring that power in front of the log of age. And this is what we come up with. That I have a linear model for the log of the age as the explanatory variable for the log of the income. Since I have a constant 1.782 times the log of the age, I have a linear equation. Remember, linear equation, we have a constant rate of growth. So that's my linear equation. Now again, I still gotta look at residuals. Okay, my residuals have a curve. This would not be a good model to use. So all of them, which of the three look like it best fits our data? Well, pretty clearly it looks like the exponential. At the highest R, the highest R squared, residual had the least pattern to it. So what income could I predict for a 47-year-old based on that data? So take a moment, look back at your data, plug in the age for a 47-year-old. And if I use our predicted income equals 6.95 times 1.05 to the power of the age, I come up with a predicted income of about $68,846. Now, if you put it in this calculator, remember it came out as actually 68.846, but our income was being measured in thousands. So don't forget, we'd have to convert that back. Now, lastly on this, we have a couple different models. If you think it's linear, you just transform, you run the regression on x and y. If you think it's exponential, you just take the log of y and run the regression on x and log of y. Everything is a power, log x, log y. Now, personally, I use the calculator. I try the other 3 models and I pick the one that's the best fit. Find the equations for linear, y equals a plus bx. If you run an exponential, it becomes y equals 10 to the power of a plus bx, which is why I'm saying y equals 10 to the power of y1. I put that linear equation, a plus bx, into y1. And lastly, power is going to become y equals 10 to the a times x to the b. Okay. Natural logs, remember, we're rapid ascent and then level off. So our logarithmics have a rapid rise and level off, sometimes a rapid decrease and then level off. Our exponentials, simply a curve, but it's a rapid rise. It doesn't drop or rise immediately. It begins off sort of level and then begins accelerating how quickly it rises. And our power curve, we said, was simply a smoother rise. It took longer to get there than the exponential growth did. So chapter 10, we'll make sure to read chapter 10. Homework was pretty light for this one, about 5 questions and then 2 on web work. This is not a section I test heavily on this test, and honestly, this is not a section that's heavily tested on the AP. Okay, focus more on chapters 7 through 9 and being able to interpret the data. If you can interpret scatter plots, that's really what we're going to focus on. Interpreting scatter plots is actually, in many ways, much more important at this stage than being able to deal with curved data. I look forward to seeing y'all in class.